Yellow is better. Okay. So you have already learned about Z mod PZ. Z mod, that is these finite fields. I have seen it in the tutorials already. If not, please raise your hand. In any tutorial group, I mean, is there any tutorial group which has not yet seen what is Z mod PZ? All of you have done this already, right? Great. And do you recall what was this? What was this? Yeah. Wonderful. Yeah. So, and we have a shorthand notation for this. You know this? That is, this we write as FP. Okay. So take this notation. FP is Z mod PZ. And how many elements are there in FP? Here. Now, how many elements are here? Do you know this? Yeah? Well, can you give me an upper bound? GL, say 2. Can you give me an upper bound for this?
Number of elements.
Number of elements. It's a set of invertible matrices over this finite field FP. Yes? PC4. Why PC4? Why they cannot be the same? For example, consider this one. Is this matrix invertible or not?
The upper bound would be like PC2 to the power 4.
Why PC2?
No, P to the power 4.
P to the power 4. Yes. So the cardinality of this is less than P power 4. Sure. Thank you. So that's the upper bound. Like wonderful. No. Nevertheless, we are Oh, because how many entries are there?
It's a 2 by 2 matrix.
It's a 2 by 2 matrix, right? So let me write down its description. Here to FP is the set of 2 cross 2 matrices A, B, C, D, such that A, B, C, and D are in FP, and this matrix ABCD. Please be a bit quiet. If you have doubts, you can ask me. And this is invertible. Okay. So we are after its cardinality, exact cardinality, not an upper bound. And our upper bound is good, but nevertheless, we would like to know exactly how many elements are there. Okay. And this is going to be a quite nice exercise. I hope by the end of today's class, we'll know the answer to this.
Is it p square into p minus 1 square?
Yes?
Is it p square into p minus 1 square?
P square into p minus 1 square? No. But we'll see what it is. Alright. So the topic that we are going to learn in today's class is change of basis. Okay. So you will wonder what this is exactly. Well, you know the hostels and the buildings, the faculty quarters, everything here are based on a ground which is soft. I mean, the soil is called soft soil, and we got this report many days after the buildings were built. So the thing is that you will see cracks on the walls, okay? And at many places the walls are going down in the soil. So there would have been ideally there would have been a better base. There should be piling, there should be more deep base of all these buildings, and this was not done. That's a pity. I mean, many of these buildings could be reconstructed later, but for now we have to go with it for several years. So if you figure there is a crack on the hostel wall, you may think that this is due to the soft soil, which we cannot remedy immediately because we cannot make the change of basis immediately. But for vector spaces, it's quite easy. Okay? To do the change of basis. So what do we mean by change of basis for a vector space? So P is a vector space over some field F, and P is a basis of P. And suppose you have another basis, B dash, another basis of, please count time in the class. Another basis of B is B prime. So now, what happens is that, well, this element of basis B are elements of V, right? Elements of B prime are also elements of V. So you can express this coming time. Alright. So write B as Bn, B prime as B1 prime dot dot Bn prime. Well, they should have the equal guardianity because the earlier day we proved that their guardianity basis of guardianities of any two bases are going to be the same. So note that now each of this V1, V2 to Vn could be expressed as linear combination of V1 prime dot dot Vn prime. Yes. Similarly, each of the bottom ones, that is this V1 primes to Vn primes, could be expressed as linear combination of V1 to Vn. Yes.
What you said?
What?
What you said?
Here we said that this basis could be expressed as a linear combination of elements in this basis, and elements in this basis as well could be expressed as a linear combination of elements in this basis. We have done this before. If you recall, when we had this spanning set and linearly independent set, we expressed the elements in the linearly independent set as linear combination of the spanning set. Please stay outside. So what we are meaning here is that this V1 prime, you could write it as, well, we were given this basis B and we are now shifting to another basis B prime. So this is our new basis, this is our old basis. Let's write the elements of the old basis in terms of the new basis. Yes?
So shifting the basis means we are writing.
Not shifting, changing the basis.
So what does that mean? Like we are writing the terms of the old basis and terms of the new basis?
Yeah, you can think like that. That is, what does a basis do? We express any of the vectors in the vector space as a linear combination of the elements of the basis. And so the coordinates, do you recall the coordinates of the vector? It's so if you write any, yeah, the coefficients, exactly. So if you are given a basis B, say B is this basis, right? V1 dot dot Vn. Now take any vector B in V. Then you could write A1 V1 plus dot 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 plus An Vn to express this V, and all these coefficients are unique. Shatik is called the direct standing outside. So these things, A1 dot An is called the coordinate of the vector. So this is called the coordinates of V with respect to the basis B. Now, when you change the basis, these coordinates change.
So we're trying to find another new coordinates.
Exactly. So what we are doing here, in this class, is that we will go from one basis to another, and then we will see how the coordinates change. Yes? So, Shravani's question was that what do we mean by change of basis? So, it's like we are going from a given basis to another, a new one, and we are, so if we go from a new one basis to another, we'll see how the coordinate vector change. So given these two bases, we'll see the relation between these two first, and then we'll see how the coordinate vectors change. And this knowledge will help us in determining the order of this Z vector. But before we do that, let's prove something which we can actually also prove using change of basis. So the first thing is that a small proposition. This you can write as aside. Aside means that which is not falling under this string, but nevertheless we could also come to this proposition using the argument that we'll learn today. Proposition 1 for today is that suppose you are in a field F and so you are given an arbitrary field, not R, some F, FP or any field F. It could be finite, it could be infinite. And you are considering matrices in those fields, some n cross n matrices over those fields. So let A be an n cross n matrix over some field F. Okay. Then the columns of A forms a basis of the vector space if n, just think of Rn, tuples with n entries. So instead of Fn or Rn, we are now taking Fn, and you could define addition and scalar multiplication exactly as you did on Rn. Yes.
Shouldn't A be invertible?
Yes, that's what I'm going to.
He's going to prove.
Okay.
But you proved it earlier, right?
Where?
In the previous class. He just told it, he didn't prove it.
I didn't prove it. So at least yes.
No, actually some groups have done it.
Maybe in your tutorial group, but in class we have not done.
No, I mean in the class, in that class you have said that. I think the group that was responsible for that, I mean,
Did they do it? Have you checked the notes?
Actually, I did.
Yeah.
I think they did.
All right. Okay. So if you think the group did it, then you could perhaps can tell us the let me write it down. The proof is simple, but nevertheless perhaps you can tell us the proof. Forms, and this is, do not take it as a punishment or saying something right. It's just an opportunity to tell the class the proof of. Okay. So then the columns of A forms a basis of the vector space Fn, if and only if, if and only if A is invertible. And not only Vikram, everybody, each of us are welcome to tell me about this proof. Maybe actually it seems Vikram knows the proof, so somebody from behind. Because I get actually quite less response from back. And that makes, that helps me build a bad habit to interact only the people sitting in the front. I shouldn't do that. So yeah, somebody from behind, please tell me something about this. How should you proceed at least? No, you are not sitting in the back. Atif? So if it is a basis, what we have to prove? You are not also sitting in the back.
With respect to him.
Okay, yeah. Sure. Yes. So, can anyone tell me what is the dimension of this? Yes. Ganesh. Why? Why the dimension of this is going to be n? Yes. Well, A is an n cross n matrix, but Fn is a vector space that we are talking about. Do you know any basis of this already? You don't? Yes, yes. Diagonal matrix. Any particular diagonal matrix? Yeah. I do not hear what I could hear from here. Someone from back? Yes? Louder? A bit louder, please. Which matrix? Columns of which matrix is giving you the basis? Yamini? Gonish again. Yeah, it's a diagonal matrix. Any particular diagonal matrix? Yes? Yes, it's in row echelon form, sure. Which one? Yes, that's called identity matrix. Okay. So you know that this Fn, how does it look like? These are just how does Fn look like? These are A1, A2, dot, 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 An. And all these AIs are from the field. AIs are from the field. So these ones, you can write it as A1 times 1, 0, dot, 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 0 plus A2 times 0, 1, dot, 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 0 and so on. Plus, wait a minute, An 0, 0, 0, all zeros and 1 here. So at least the columns of the identity matrix spans this. Okay. And suppose now there exists a linear combination. So what you have to do now to show that this is a basis?
Show that not all of
That they are linearly independent. So now assume that there exists such a linear combination which is equal to 0. Okay. So if such a linear combination A1 times this, A2 times this, An times this is equal to 0, then what can you tell about this coefficients A1, A2, all has to be 0. It's clear from the from the definition, right? That is, if this is equal to 0, then that's the only possibility is that each of A1, A2, etc. A is equal to 0, right? So by definition, the identity matrix, the columns of the identity matrix are linearly independent and they are spanning the space Fn. So it must be a basis, and that's why we say not N here, excuse me. So that's why we say that the dimension of this is N. Okay. Not because it is we write an N here, because there exists a basis of cardinality N which spans this space. So that's why it's of dimension N. And now you are given, instead of the columns of the identity matrix, you are given the columns of an arbitrary matrix A. Okay. What do you have to show now?
There is no linear relation.
Alright. Suppose you can show that there is no linear relation between them. How do you show that it spans the space?
By showing that the basis can be represented, can be transformed into A.
From?
So we have the identity matrix. If we can do elementary transformations on that to get A, then that means we change the basis from the identity basis to A.
So that's a proof which we will do after we do change of basis. Without doing change of basis. Actually.
So we can take any vector y in this Fn.
Yes.
And we are given that A is invertible, right?
Right.
So we can we can take A inverse y.
Well, it's actually we have to show that it is invertible if and only if it forms a basis.
Yeah, so first we show that it forms a basis, this implies it is invertible, and then we show that it is invertible, this implies it forms a basis.
Okay, so which assumption you are starting with?
I am starting with that it is forming a basis, this implies it is invertible.
So people sitting in the back, please shut down the computer. What are you doing there? Okay, write on the tab, but not in the. So please keep your attention here and not on the screen. So what I'm saying is that look at your friends sitting in the here or here. They are not giving me the proof. We are arguing back and forth, okay, to get the proof. And I want to get this arguing from also. Please take part in this as well. Try to think out loud. We may be wrong. I may be wrong. It doesn't matter.
So can we prove this by contradiction?
Yeah.
Prove it by contradiction. If it prove that it's suppose A is not invertible.
Yes.
Prove that the inverse exists. Hence it is invertible.
Okay, yeah. So you were starting with the assumption that A is
Not invertible.
okay, and that is it forms a basis.
It forms a basis.
All right. Okay. So what does it mean by it forming a basis?
It's invertible.
You are starting with the assumption that A is not invertible.
Then the end result should be that it not forms the basis.
So Atif, we are running out of yellow chalks now. We have to use white. So A is okay. So A is not invertible. Okay.
So
We are starting with this assumption. So this is our assumption. And what we are going to do, we are going to show that the columns of A cannot form a basis.
I mean the contrapositive of the forward shift.
Yes, right. So suppose now that A is not invertible and the columns of A forms a basis of B. What does it mean? They span B. What else? They are linearly independent. So, yeah, Srinivas, proceed from here. So they span V and they are linearly independent. Now,
So if they are linearly independent, it means that they are okay. That's what we have to prove.
so you have started with the assumption that A is not invertible, and you are assuming that the columns form a basis. That is, they span V and they are linearly independent. Now, what we are trying to do? We are trying to get a contradiction. So get a contradiction from here.
Contradiction would probably be that
So now we can't. If we take that as a matrix,
Yeah,
if we take it as a matrix, we need to show that there are no non-zero rows in a reduced row echelon form. So
Non-zero?
it is. If we take the basis,
okay.
if we
So,
add them up,
so let's write A as now the columns of A we are writing as the first column V1, second column V2, the last column Vn.
so
And then a linear combination would look like C1 V1 plus Cn Vn. And this is equal to 0. Proceed from here.
so if we have a reduced row echelon form of an n cross in matrix A.
Now AC is equal to 0, right?
Yeah.
Yes, Akshwit was trying to say for a long time.
So we can write it in form of A cross X, where X is all the coefficients.
Alright, yeah. Very good. So this is X is equal to C1 Cn. Right? And then,
Coefficient.
yeah.
So this should be AX is equal to 0.
Wonderful, yes. This is Ax equal to 0.
And since A is not invertible, it would be having infinite number of solutions.
Sure.
So this means that there would be a non-trivial solution.
Linear relation between V1 to Vn. Contradiction. So they are not forming a basis, you see. Is this argument that, well, let me write it down and then tell me whether this argument is clear to you. So we assume that A is not invertible. That means this equation is Ax equal to 0. What it is giving? It is giving such a thing, a linear relation among the columns of A. Right? Is this point clear to all of you? And now note that if A is not invertible, such an equation will have infinitely many non-trivial solutions. Okay? So if A is not invertible, this equation has, well, a non-trivial solution would do for us. Non-trivial, that is non-zero solution. What does it mean? That this Ax equal to 0 and there exists a non-trivial solution of this? That there is a linear relation among the columns of A. That implies there exists a non-trivial linear or just linear relation. By linear relation, we are meaning that not all the coefficients are 0. Among or between, but among is fine. The columns of A. And that's a contradiction because A was supposed to be a basis. So we see that A is not invertible implies that the columns of A cannot form a basis. Right? What the opposite thing will mean? That is, if the columns of any matrix is forming a basis, it should be invertible. Okay? Now, come in a direct way. So, what we have seen shown here is that if the columns, so we conclude here, if the columns of A forms a basis, that implies A is invertible. Okay? So this is implication from here to here. Now assume that A is invertible. Why the columns of it should form a basis? If again, Punavata.
If A is invertible, then A equals 0 will have only one trivial solution.
Right?
Which means the vectors are columns are linearly independent.
Wonderful. So the columns of A is invertible, it immediately implies that this equation has only the trivial solution. Right? So the columns of A are linearly independent. How to prove that it spans P? Ashwin, you wanted to say something?
No, let me.
Okay.
First, I think that there is a general vector from in that vector space,
Yes.
which is linearly independent with the other same vectors, and show that you can number.
Any other idea? Or
A has the cardinality of the basis.
A has the cardinality of the columns of A, the cardinality of the columns of the set of columns of A has the cardinality of the basis. Wonderful, very good. So that finishes the proof of this. I'm not writing it down because I mean it will take some more time and we should say what is change of basis. So is the argument that Punnabrata gave and Orko finished. So is it clear to all of you? Atif, you wanted to say something? Right. Actually, they are proceeding from there, but nevertheless, here we are. Let this be one proof. That is, we assumed A is not invertible, and we concluded that the columns of there is a non-trivial linear relation. So we have such an implication, and now we are going to go back. But it's exactly that equation with which Punnabrata gave his argument. All right. Yeah. Very good. Yes. Sure. Exactly. So if x equal to 0, so basically it is you are saying that x equal to 0 is the only solution because A is invertible. Multiply it with inverse of this, and you get x equal to 0. Very good. Yeah. Alright, yeah, sure, this works. Yeah, but this multiplying with A inverse, this is actually also the same logic I think that Punnabrata gave. That is, since it is invertible, the only solution is x equal to 0. So now we talk about the change of basis at last. Sorry, this was the last board. Maybe I cleared this board first. The question.
So can we also see if A is invertible? That means the reduced workload form of A will have no non-zero rows, and hence all the rows are bases.
Okay. Sure. That's also good. That's perfectly good.
But here we have made, while we talk about invertible,
Yes.
we mean that we eventually do, to find it, we do row operations, right? We have made no explicit reference to the determinant, right?
No, but nevertheless, we have proved in the intro that is in the introductory class, that is invertible if and only if the determinant is non-zero.
Yes, but we haven't really defined the determinant, right?
Well, it's fn. I mean, the determinant, the definition of determinant, what you have, which you were carrying from the previous class, previous year, it runs also for any field.
So we can just define it by the Laplacian.
You can define it in several ways. Okay? So you can list a set of properties, define determinant by that. That's the way Artin does. Or you can use just a grammar
Yeah,
suite
but
and
then you have to show the existence that
Exactly.
such a function, such a mapping
Exactly.
exists.
Sir, can you please explain that how you proceed after you say that x is equals to a null vector?
x equal to
In the second, in the converse.
in the converse, that is if x is equal to 0. Well, if x is, I mean, if the only solution of this is that x is 0, that means the columns of A are linearly independent, right? So you are having a set of linearly independent vectors of cardinality n. N was its dimension, you see.
But you need to show that the cardinality of that set is n. Or
Which
is that you assume that?
No, I didn't assume. This is an implicit matrix. There in columns, and then we already argued that the coordinate of this is n because it has a basis of the columns of the identity matrix is forming a basis of this, right? So you know the coordinate of one basis of this.
So I can claim without proving that the cardinality.
That it spans the entire thing. So now change of basis. It's quite easy. You had a basis B and you are changing to some, well, you had some basis B and another basis B dash is given to you. Now you want to express each of the elements of the old basis B as a linear combination of the elements of B prime. That is, suppose V1 is your element here and you would like to write that this is equal to some C1 V1 dash plus whatever Cn Vn dash. So exactly how we expressed the linearly independent set in one of the previous classes as a linear combination of the spanning sets. Okay. So you recall how what we did? We denoted the, well, we wrote these things. That is we listed the linearly independent vectors in linearly independent set and then wrote them as a hypervector, wrote the other thing as a hypervector, multiplied on right with a matrix, which was giving the linear combinations expressing the elements of the linearly independent set. Okay? We will do exactly the same thing here. Okay? So this is our old basis, and you can write this as here we write B as V1 dot Bn, the hypervector, okay, containing the elements of B, and then we are trying. We would like to express this. So this is the set that will express as linear combination of B dash. Okay. So okay, we should write it on the left. Excuse me. So this is how we proceeded, right? Earlier, so this is our V1 to Bn, and then we had B dash here, that is B1 dash Bn dash, and then we multiplied this with the matrix whose columns were given the linear combinations which express this. If you recall it. So we multiplied it with some matrix which we now denote by P, and how does it look? So P is P11. Well, I would just write one column. Actually, we have already wrote one column of this. So if you multiply this with the ith column, you are getting the ith vector here. Okay? So these are depending on the ith columns. C, this instead of Ci, we should write Pi, P1i, Pni, etc. ith column. Okay, and these times the ith column will give you the ith vector here.
So P is an n cross n matrix.
P is an n cross n matrix, of course, because this is n, this is n, both of n here. Earlier it used to be some other matrix. I mean, on one side the coordinate of this should be equal to the coordinate of this, and on the other side it should be the coordinate of this, because the multiplication should be defined and you will get exactly this number of elements. So earlier it was a little bit different, because this n and so at one thing here it was n, here it was m, but now both are the same. So you're going to get here an n cross n matrix. And this matrix, I mean, multiplying with this matrix from the right hand side, this matrix of course belongs to F n cross n, that is it's an n cross n matrix with entries in F. Okay? The notation for this is also this one. We often would write m n F for matrices of square matrices of size n cross n with entries from F. Yes, Palvi.
You're saying like something about what were you saying about n? Like there was n on one side and m on one side.
Oh, these cardinalities of the basis.
Yeah.
In the case of linear, independent, and spanning
Before
sets.
defining dimension, right?
Before defining dimension, right? If you, I mean, we did this. I asked you to remember less, because L was less than equal to S.
Yes.
If you remember, and there on the left hand side there was the linearly independent set. On the right hand side there was a spanning set times some matrix, and each of the columns of the matrix was given the linear combination of the spanning set, which was expressing the linearly independent set. So we are doing exactly something similar here. Yes, doubts or questions, please. Okay. So this one, Pn n, we write that this is inside. We actually use this what we have written below this notation more than this F n cross n, to say that this is some matrix, some n cross n matrix in F, okay, with entries from F. And now this matrix, by which we are going from one base to another, this would be called the matrix of change of bases. Okay? P is called the matrix of change of bases. Okay? All right. Yes, Vikram.
So, why do you write that the P matrix should belong to M and F?
Because, well, what is this matrix V? This vector space V. We haven't defined the field. Okay, so we are saying that this vector space V is over some field F, some arbitrary field F. Okay, and then what does it mean for V to be over the field F? That is, if you are given any basis V or V1 to Vn of this vector space, every vector is a linear combination of that basis with coefficient from that field F. So that means that this is the actually coefficient matrix, right? Every column is giving a coefficient. So where they are coming from? They are coming from the field, and that's why we write M and F.
I am asking that how, I mean, is that what is the case where the P matrix would be a null matrix or the
We are coming to that, but at first, is the definition clear to you? Okay, so take that for the time. Take this to be the definition. That is the change of basis. So we'll get its property soon. That is whether it can be the null matrix or not. We'll see that.
It cannot be, right?
It cannot be. Yes.
Because it has to be convertible.
Wonderful. Yes, Palvi. Why?
Because like if I'm changing from one basis to another, I can obviously change from that
Sure.
basis to back.
Very good. Very good. So Vikram, that so note that what argument he gave. So B dash is the new basis, and we are expressing B in terms of this. So we can write B dash B. Well, we would write this to say that we are writing. I mean, this third bracket would just explain. And no. So by this we would only say that we are expressing the elements of B dash as a hyperdegree. B12, B1 prime to Bn prime. Okay? And we would write also this one. And if you are quite accustomed to the notation, you may sometimes omit this, but this will be understandable. That B, the basis B, is given by B dash B. That is, you are writing the elements of B dash as a hypervector, multiplying it with this matrix P. to obtain the elements of the older basis B. So this is the chain of basis matrix. And now, can you tell me how should the coordinate of any vector would look like in terms of this basis B? So suppose G is your an arbitrary vector, and then how the coordinates of V should be related with this B?
So linear combination of all the vectors in B multiplied by B.
No,
So
not
V-
P. P is the matrix of change of basis. I am not talking about the new basis.
So,
I'm talking about the
linear
old
combination
basis.
of vectors in B.
Yes.
V1 plus V2.
Right. So you could write that as V1, V2 to Vn times some column matrix, column vector, right?
Yeah.
And that column vector would be the coefficients, those coefficients which is giving this V.
Yes.
Right? So what I am saying is that this V, an arbitrary element of the vector space V, you can write it as C1 V1 plus dot 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 plus Cn Vn. And this one you can also write as V1 dot 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 Vn times C1 dot 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 Cn. Right?
Yes.
Now note that this one we denote by this bracket B.
Yep.
Okay? So this is the definition of bracket B, and then you have this B times, if you call this coefficients x, so this is Bx. Okay? Now after you have changed the basis, what happens? Where should I write? Maybe the upper part we can use, right? Because this is just the same thing that we have written here. Yes. Which one? Shami? Yes, yes. Here? Okay, here I am just trying to make you understand what I mean. Suppose you have a vector V and you would like to express it in terms of the basis B, then the coordinates can be written as V equal to Vx. So V is C1 V1 plus dot dot Cn Vn. And then you can write V1 V2 Vn times C1 C2 to Cn. This is your x, so V times x. So we can write this V as V times x. Right? We did just. And then what is the relation between V and this V prime?
V dash P is equal to V.
Yes, V dash P is equal to V, right? So we just replace it. We replace this with V dash P. This one and this one are equal, right? Okay. Times x. Alright. These two things we are just replacing V with V dash P. So now, with respect to V dash, what is the coordinate vector of V? Very good. So, if we denote by x dash, so let x dash be the new coordinate vector coordinates. You also call it coordinate vector. Okay? Coordinates of V, that is with respect to V dash. Then it is related with the old coordinates by the relation x dash is equal to, well, can we write that x dash is equal to px? So can we write? We saw that px would work, but nevertheless, will it be the, will it, I mean, is it the, yes? Which one? P is unique, but nevertheless, what I am saying is that is x dash uniquely defined as px? Or
So
that
we can take it to the other side and we can take out x and maybe we can do something from there.
I get value.
well, every vector is a unique linear combination of the basis elements. What does it mean?
You can't say this.
We can always say this because P is the matrix of change of basis. you're multiplying with x, you are getting some expression, okay? And that should be the unique expression for v with respect to the new basis, because there is only one expression. So if you are having some expression which are representing v in terms of v, then this is going to be that unique expression.
So how do we sort of show this like rigorously, like that?
We just said it, and what we said is completely rigorous. We said that every vector is uniquely representable as a linear combination of the basis vectors. Did we prove this in earlier class?
Yes.
So now suppose that this is your vector v. This is your new basis, and this is the linear combination. This is a column vector, right? This is a linear combination of the new basis. So it's a linear combination of the new basis that is expressing your vector v. Right? So that linear combination is going to be the unique linear combination which is expressing v in terms of this basis. Okay? I mean, is this rigorous enough, or is there any gap in the argument?
I mean, I think I'll just have to see it a couple of more times when I'll.
Yeah, so this is because every vector in V is expressible uniquely has a unique linear, is expressible as a unique linear combination of the basis vector, and whichever basis you are considering, doesn't matter. It is up to, with respect to that basis, the expression is going to be unique.
So in this case, we are considering the old basis, right?
Which one?
I mean, the old basis.
Here we are considering the old basis, and now while we are writing this one, we are considering the new basis. This is the expression with respect to the new basis, and this is the new coordinate. The new coordinate and the old coordinate should be rewritten in this one. Of the basis. So now let's go back to the thing, that the proposition that we have done earlier. But at first, change of basis is quite a simple thing. You go from old basis to the new basis just by multiplying with the matrix of change of basis. Ganesh, are you paying attention? So this is the matrix of change of basis. You go from the old basis to the new basis by multiplying on the right with the matrix of change of basis. And then this is the old coordinate, this is the new coordinates. You get it by multiplying with the change of basis matrix on the left. So these are just two simple relations that the derivation is quite simple. You don't even have to learn it by rote. You can remember the proof and how we proceed. So now what we are going to say, that is, earlier we said that columns of a matrix forms a basis if and only if the matrix is invertible. Now this will be quite easy to do after we have done this. So I'm just working out the definition of matrix of change of basis. And suppose you are given the columns of some matrix A. Okay? Suppose that's a basis. So it was an argument given by Ashmit, I guess. And we said that did Ashmit give it or you gave it, right? Alright.
Oh, I did. But then you said we hadn't introduced this yet. I'm sorry.
Alright, yeah. What's your name?
Rithima.
So yeah, this was your argument. That is, if we start with some matrix A, and then suppose we write down its column as elements of the basis, and we take I to be another basis, the columns of the identity matrix. So I is, say our old basis is I, and our new basis is going to be A. Okay? So what should be the relation between these two? I we can write here, and that would be equal to A times
A inverse.
A times P.
Oh, some.
P is the matrix of change of basis.
Right.
Okay? So you see, this is the old basis. I mean, the columns of this is the old basis, and this is the new basis. What do you conclude from this equation?
That A is invertible.
Yes, A is invertible. The change of basis matrix should also be invertible. I mean, we get the invertibility of everything from this. And also note that there is a nice relation. That is, the change of basis matrix here is just the inverse of A. So this is one line. If we use the change of, I mean, well, other proof was not also quite, I mean, at all difficult, but this is another way. Like that.
Say it once again.
So this is our new basis, B dash. This is our old basis, B. How we go from one to another? B dash times P, the change of basis matrix, is giving you B. B is the old basis, right? And so if you now write it down, so this equation, I'm just writing this equation and nothing else. And we should have a relation like this. For the columns of this to be a basis of our vector space, we should have A times the change of basis matrix equal to identity. By this relation of change of basis.
Oh, I know.
And now this implies, I mean, if A times this is an n cross n matrix, this is an n cross n matrix, you are getting A times P is equal to identity. And this cannot happen, I mean, if the determinants of this or this is 0. So the determinant of this is non-zero, the determinant of this is non-zero, that means they're both of them should be there. Yes.
Sir, you were saying about how P would be an n cross n matrix.
P is an n cross n
for this example. So if we had something like n minus 1 cross n matrix,
why? You are changing from basis to basis,
so
right?
we will be changing dimensions, like how you are talking about how 3D photos are getting into 2D in the phone.
That's called a linear transformation. We will do that.
So this is not linear transformation.
Which one? This is a change of basis. So we'll learn linear transformation soon. Once we finish the basics of vector space, we'll go into that.
But is this a linear transformation?
Which one?
The one we just did.
This is change of basis. Well, actually, you can think of this. It's a map. What are linear transformations? Before we define them rigorously, they are maps from vector spaces to vector spaces. So, if you are changing from a basis to another basis, it's like you are considering the vector space given this basis. Now you are considering the same vector space given this basis. Okay. So it's a map from the same vector space to same vector space, but it's an identity map. Okay. So we are not changing the individual vectors. We are mapping the individual vectors to the same things. Right? So it's somewhat different from what you mean by linear transformation. Here it's it's the same vector space. We are expressing the same vector, but with different coordinates.
Okay. So for change of basis, what you're doing is saying that if I have a vector and I'm mapping to itself,
Yes.
like what I'm doing is original coordinates to new coordinates.
Yeah.
So what you're doing, you're basically distributing over the basis vector. So you're seeing how it.
I am just writing that vector, the given vector, in terms of the new vector, new basis vectors. So only the coordinates changing. Coordinates are changing, not the actual vector. So for example, just one minute, I am giving you an analogy. That is, you can express the same number with respect to different bases. Right? You can express this in base 10, you can express it in base 2, base 8, whatever base you wish. So each time, the expression that you will get, the digits will be different. But nevertheless, the number remains the same.
Like Cartesian's vector remains the same and you even rotate.
Yeah, so here, the vector V remains the same, only its coordinates change.
Okay.
Alright, is this point clear to all of you? Okay. Now note one thing, that this way, given a basis B, well, this also means that if you multiply, you can express B dash in terms of B, right? So that means if you multiply it with some matrix of change of basis from B dash to B, that will be some B times Q equal to B dash. And what is going to be the relation of that Q with B? Wonderful. They are going to be the inverse of each other, because of this, that is, every vector is uniquely expressible as a linear combination of the basis vector. So if you multiply with Q, so that would give you this times P times Q equal to B prime. So that will mean that P times Q is giving you another linear combination of B prime, which is giving the elements in B prime itself. And the elements of B prime are given by the, so say Vi dash. Okay? That is given by the linear combination Vi dash. Everything else you put to 0. Yeah. Follow.
But this argument that we have another matrix, if we go from one basis to another, we have matrix P.
Right.
We're going back, we have another matrix Q.
Right.
That argument hinges upon the fact, right, that because they are of finite dimension.
Yeah, sure, of course.
Because you'll have a pigeonhole, then you can it's a bijective mapping. You can't show that for entire.
Yes, I mean actually we also used it while Orko gave the argument, that is we have two linears, a basis and a linearly independent set of the same cardinality. Then it has to span the thing because it should be a basis. So in finite dimension vector spaces you have this advantage. That is, you don't have to check whether it's linearly independent and whether it spans both.
So can you repeat what you just said here?
Yeah.
Just earlier.
Again, okay, I'll write it down very shortly. So here, what we wanted to say is that here, from there, B dash P is equal to B, and suppose B Q is equal to B dash. Then we are trying to argue that these are inverses of each other. Because, multiply it with Q on the right hand side, that would mean that B dash PQ is BQ, which is giving you B dash again. Right?
That means inverse of P exists.
Inverse of P exists and Q is the inverse of P. We have seen argument
that for all P, the inverse exists.
all P which are change of basis, the matrices which are change of basis matrices, all of them should be inverted.
So you previously assumed that P should belong to the set of
M and F. Now it should be belonging to GL and F. Right. Yeah. So P, where was it? P dash PQ should be equal to B dash. Okay. And this immediately implies that PQ is the identity matrix because the columns of the identity matrix are expressing the elements of B dash uniquely. And in particular, as Vikram just commented, in particular, this would mean that the change of basis matrix P or Q, they are elements of GL and F. Okay?
Can we use that to show that the change of basis matrix is unique for any given change of basis?
What? Change of basis matrix?
If we have changing basis, can we use this to show that change of basis?
You don't have to use this. You just use this one. That every vector is uniquely expressible as a linear combination of the basis vectors. So these are just linear combinations of basis vectors which are representing this one. So this is well defined, uniquely defined. B and B dash. Okay, that's all for today's class.